Learning objectives. In this chapter, the user would learn the following aspects of sets, relations, and functions. Sets, subsets, and operations on sets, finite and infinite sets. Relations and properties of relations, equivalence, compatibility, partial order relation, poset, least upper bound, greatest lower bound, maximal and minimal elements of a poset. Functions, inverse functions, composition of functions, recursive functions. Sets. A set is a distinct collection of objects. The objects are called elements. We will develop more fully the definition of sets, the properties of sets, the operations on sets. Sets are fundamental discrete structures. Definition. The objects in a set are called elements or members of a set. A set is said to contain its elements. Notation. For a set A, X belongs to A. X is an element of A. X not belongs to A. X is not an element of A. For example, if A equal to 1, 3, 2, 5, 3 belongs to A, 3 is an element of A. 7 not belongs to A. 7 is not an element of A. Terminology. A equal to 1, 2, 3, 4 are called elements. B equal to 1, 2, 3, 4 are also called elements. Two sets A and B are equal if they contain the same elements. We write A equal to B. A equal to 2, 3, 5, 7. B equal to 3, 2, 7, 5. A equal to B. Order does not matter. If a set contains the same elements as another set, the sets are equal. A equal to 2, 3, 5, 7. B equal to 2, 2, 3, 5, 3, 7. A equal to B. Repetition of elements does not make any difference. However, A equal to 2, 3, 5, 7. B equal to 2, 3. The elements 5 and 7 are not available in a set B. Hence, A not equal to B. Multiset. A multiset is a set where you specify number of occurrences of each element. A equal to 5, 6, 7, 8 is called set. A equal to 5, 6, 5, 7, 6, 7, 7, 8 is a multiset. We clearly explained in the picture. M1 occurs A1 times, that is called 5 occurs 2 times. M2 occurs A2 times, that is called 6 occurs 2 times. M3 occurs A3 times, that is called 7 occurs 3 times. M4 occurs A4 times, that is called 8 occurs 1 time. Set builder. The set builder notation O equal to X such that X belongs to Z and X equal to 2K for some K belongs to Z. O is the set that contains all X such that X is an integer and X is even. We clearly explained in the picture what is the meaning for O, what is the meaning for X, etc. Intension. A set is defined in intension when you give its set builder notation. O equal to X such that X belongs to Z and 0 less than or equal to X less than or equal to 8 and X equal to 2K for some K belongs to Z. Extension. A set is defined in extension when you enumerate all the elements. O equal to 0, 2, 4, 6, 8. Substitute the values K equal to 0, 1, 2, 3, 4. We getting the values 0, 2, 4, 6, 8. Venn diagram. A set can be represented graphically using a Venn diagram. A Venn diagram or set diagram is a diagram that shows all possible logical relations between a finite collections of objects. Terminology and notation. A set that has no elements is called the empty set or null set and is denoted by pi. A set that has one element is called a singleton set. For example, A with brackets is a singleton set. A without brackets is an element of the set A. Definition. A is said to be a subset of B and we write A is a subset of B if and only if every element of A is also an element of B. That is, we have the equivalence. A is the subset of B. If and only if for every x belongs to A implies x belongs to B. A set A that is a subset of a B is called a proper subset if A not equal to B. For example, A equal to 1, 2, 3, 4, 5. Number of elements 5. B equal to 1, 2, 3, 4, 5, 6, 7, 8. Number of elements 8. Therefore, A not equal to B. That is, there is an element x belongs to B such that x not belongs to A. We write A is the subset of B. For example, consider a set 1, 2, 3, 4, 5. Then 1, 2, 4 and 1 are proper subsets, while 1, 2, 6 and 1, 2, 3, 4, 5 are not. Definition. Set operations. Intersection. The common elements of two sets A intersection B equal to x such that x belongs to A and x belongs to B. For example, A equal to 1, 2, 3, 4, 5. B equal to 3, 4, 5. Therefore, A intersection B equal to 3, 4, 5. If A intersection B, the sets are said to be disjoint. The common for all sets given is called as intersection. Union. The set of elements that belong to either of two sets. A union B equal to x such that x belongs to A union x belongs to B. For example, A equal to 1, 2, 3, 4, 5. Then B equal to 5, 6, 7. A union B equal to 1, 2, 3, 4, 5, 6, 7. We just want to join all the elements in this example. That is the meaning for A union B. All the elements in the given set is called as union. Complement. The set of elements in the universal set that do not belong to a given set. A equal to x belongs to U such that x not belongs to A. For example, U equal to 1, 2, 3, 4, 5. A equal to 1, 2, 3. Then A dash equal to 4, 5. How are we getting this? We just want to compare the elements with the universal set. We generally call U as universal set. We just comparing A and U. What are elements not having in A? We just want to write it. That is called A dash. Difference or relative complement. The set of elements that belong to a set but not to another. A minus B equal to x such that x belongs to A and x not belongs to B equal to A given B. For example, A equal to 1, 2, 3, 4, 5. B equal to 3, 5, 7, 9, 10. A minus B equal to 1, 2, 4. Then B minus A equal to 7, 9, 10. We have to write only the elements or not in B. Symmetric difference. Given two sets, their symmetric difference is a set of elements that belong to either one or the other set but not both. Symbolically, A delta B equal to x such that x belongs to A union B and x not belongs to A intersection B. A delta B equal to A union B minus A intersection B. Then A delta B equal to A minus B union B minus A. A delta B is shaded. Example. If A equal to 1, 2, 3, 4, 8. B equal to 2, 4, 6, 7. Then A delta B equal to A union B minus A intersection B equal to 1, 2, 3, 4, 6, 7, 8 minus 2, 4. Then finally A delta B equal to 1, 3, 6, 7, 8. Properties of sets. Associative laws. A union B union C equal to A union B union C. A intersection B intersection C equal to A intersection B intersection C. Commutative laws. A union B equal to B union A. A intersection B equal to B intersection A. Distributive laws. A union B intersection C equal to A union B intersection A union C. A intersection B union C equal to A intersection B union A intersection C. Identity laws. A union pi equal to A. A intersection universal set equal to A. Complement laws. A union A complement equal to universal set. A intersection A complement equal to pi. That is called null set. The analogy between unions and intersections of sets and addition and multiplication of numbers is quite striking. Like addition and multiplication, the operations of union and intersection are commutative and associative, and intersection distributes over unions. However, unlike addition and multiplication, union also distributes over intersection. Two additional pairs of laws involve the special sets called the empty set pi and the universal set u, together with the complement operator. The empty set has no members and the universal set has all possible members in a particular context. Properties of sets. Idempotent law. A union A equal to A. A intersection A equal to A. Domination laws. A union universal set equal to universal set, that is denoted by U. A intersection pi equal to pi. Absorption laws. A union A intersection B equal to A. A intersection A union B equal to A. As noted above, each of the laws stated in the proportion 3 can be derived from the 5 fundamental pairs of laws stated above. As an illustration, a proof is given below for the idempotent law for union. Proof. A union A equal to A union A intersection universal set by the identity law of intersection equal to A union A intersection A union A complement by the complement law for union equal to A union A intersection A complement by the distributive law of union over intersection equal to A union pi by the complement law for intersection equal to A by the identity law for union. The following proof illustrates that the dual of the above proof is the proof of the dual of the idempotent law for union, namely the idempotent law for intersection. Proof. A intersection A equal to A intersection A union pi by the identity law for union equal to A intersection A union A intersection A complement by the complement law for intersection equal to A intersection A union A complement by the distributive law of intersection over union equal to A intersection union by the complement law for union equal to A by the identity law for intersection. Intersection can be expressed in terms of set difference. A intersection B equal to A given B. Properties of relations. Let A and B be sets. A binary relation from A to B is a subset of A cross B. Let R be a relation. If A, B belongs to R, we write A related to B. Example. Let S be a set of students. Let C be a set of courses. Let R equal to S, C. Students, S is taking course C. Many students may take the same course. A single student may take many courses. Functions as relations. Functions are a kind of relation. Let function f A tends to B. If f of A equal to B, we could write A, B, then f of A cross B. Probability of A cross B equal to set of all relations from A to B. let f equal to the set of all functions from a to b. F is a proper subset of a cross b. Relations on a set. A relation on a set A is a relation from A to A. Examples of relations on R. R1 equal to A comma B such that A less than or equal to B. R2 equal to A comma B such that B equal to sort of A. A relation R on A is reflexive. For every A related to A, symmetric. For every B, A related to B tends to B related to A. Let S be a set of people. Let R and T be relations on S. R equal to A comma B such that A is a sibling of B. T equal to A B such that A is a brother of B. Antisymmetric. For every B, A related to B and B related to A tends to A equal to B. For every B, A not equal to B tends to A comma B belongs to R union B comma A not belongs to R. Example, L equal to A comma B, A less than or equal to B. Transitive. For every A, for every B, for every C, A related to B and B related to C tends to A related to C. Composition. Let R be a relation from A to B. Let S be a relation from B to C. The composition is S composite to R equal to A comma C such that there exists B, A related to B and B related to C. Let R be a relation on A, R1 equal to R, Rn equal to Rn minus 1 composite to R. Let R equal to 1, 1, 2, 1, 3, 2, 4, 3. Relations on a set. The word graph above is used as a verb. Let A equal to 1, 2, 3, B equal to 2, 3, 4. Let R be a relation from A to B where A comma B such that A divides B. Representing relations using matrices. Let A equal to A1, A2, etc. An be a finite set. Then we can represent a relation R over the set A using an n by n matrix, where entry Aij equal to 1 if Ai Aj belongs to R, Aij equal to 0 if Ai Aj not belongs to R. Example, let A equal to 1, 2, 3 and R equal to 1, 1, 1, 2, 2, 3, 3, 1 is the 3 by 3 0 1 matrix that represents the relation R. Representing relations using matrices. This representation can be generalized in the obvious way to represent a relation R from A to B where both A and B are finite sets with m and n elements respectively. Then an m by n 0 1 matrix can be used to represent the relation R. Example, let A equal to 1, 2, 3, B equal to A, B. Then R equal to 1, B, 2, A, 2, B. Then the matrix is shown by the figure is by the 3 by 2 0 1 matrix that represents the relation R. We can use the matrix representation to store relations in a computer and efficiently perform certain operations on relations using matrix operations. Representing relations using diagrams. While the matrix representation is convenient for working with relations in a computer, a D-graph representation is a more visually appealing way to represent a relation on a finite set. Let A equal to A1, A2, A3 and let R be a relation on A. For the D-graph representation of R, we use a labeled dot to represent each element of A. Then for each pair, Aj, Ak That is, in R, we draw an arrow coming out of dot AJ and that points to dot AK. Example, let A equal to 1, 2, 3, 4 and R equal to, that is called relation, 1, 2, 2, 1, 2, 2, 3, 4. Representing relations using D graphs. Reflexive. The relation represented by a D graph is reflexive if and only if there is a loop at every vertex. Reflexive. The relation represented by a D graph is irreflexive if and only if there is not a loop at any vertex. Symmetric. The relation represented by a D graph is symmetric if and only if all arrows other than loops come in pairs with reverse direction. Antisymmetric. The relation represented by a D graph is antisymmetric if and only if there are no pairs of arrows with reverse direction. Transitive. The relation represented by a D graph is transitive if and only if there is an edge from A to B whenever there is a path from A to B for all nodes A and B. Equivalence relation. An equivalence relation on a set S is a relation on S which is reflexive, symmetric and transitive. In general, an equivalence relation results when we wish to identify two elements of a set that share a common attribute. The definition is motivated by observing that any process of identification must behave somewhat like the equality relation. The equality relation satisfies the reflexive x equal to x for all x, symmetric x equal to y implies y equal to x, and transitive x equal to y and y equal to x implies x equal to z properties. Example, let R be the relation on the set of real numbers or, in example, prove that if x related to x dash and y related to y dash, then x plus y related to x dash plus y dash. Proof. Suppose x related to x dash and y related to y dash. In order to show that x plus y related to x dash plus y dash, we must show that x plus y minus x dash plus y dash is an integer. Since x plus y minus x dash plus y dash equal to x minus x dash plus y minus y dash, and since each of x minus x dash and y minus y dash is an integer by definition of R, x minus x dash plus y minus y dash is an integer, thus x plus y related to x dash plus y dash. Equivalence classes. Given an equivalence relation or on a set S, we define the equivalence class containing an element x of S by x equal to y such that x comma y belongs to R equal to y such that x related to y. Let R be an equivalence relation on A and let A, the set A equal to x such that A related to x is called the equivalence class of A. The element in the bracket in the above notation is called the representative of the equivalence class. Example, let S equal to 1, 2, 3 and R equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. Then 1 equal to 1, 2, 2 equal to 1, 2, 3 equal to 3. Let S equal to R and R equal to x, y such that x square equal to y square. Then 0 equal to 0, 1 equal to 1, minus 1, 1 by 4 equal to 1 by 4, minus 1 by 4, x equal to x, minus x. Equivalence theorem. Let R be an equivalence relation on a set A, then the following are equivalent. 1. A related to B 2. A equal to B. 3. A intersection B not equal to empty. Suppose A comma B belongs to A and A related to B, we must show that A equal to B. Suppose X belongs to A, then by definition of A related to X, since R is symmetric, and A related to B related to A, since R is transitive, and we have both B related to A and A related to X, B related to X, thus X belongs to B. Suppose X belongs to B, then B related to X, since A related to B and R is transitive, A related to X, thus X belongs to A. We have now shown that X belongs to A if and only if X belongs to B, thus A equal to B. We have seen now proof 1 to 2. Now 2 to 3. Suppose A comma B belongs to A and A equal to B, then A intersection B equal to A. Since R is reflexive, A related to A, that is, A belongs to A. Thus, A equal to A intersection B equal to empty. 3 to 1. Suppose A intersection B equal to empty, then there is an X belongs to A intersection B. By the definition, A related to X and B related to X, since R is symmetric, X related to B, since R is transitive, and both A related to X and X related to B, A related to B. The purpose of any identification process is to break up a set into subsets consisting of mutually identified elements. An equivalence relation on a set A does precisely this. It decomposes A into special subsets called equivalence classes. 0 equal to Z, the set of integers. 1 by 2 equal to n by 2, m is an odd integer. Pi equal to pi plus n, given n is an integer, equal to pi plus n for any integer n. These ideas are summed up in theorem when we say several statements such as P1, P2 and P3 are equivalent. We mean P1, P2, P3 is true. Notice that in order to prove that the statements are mutually equivalent, it is sufficient to prove a circle of implications such as P1 tends to P2, tends to P3, tends to P1. This is how we set up the proof of theorem. Partition. A collection S of non-empty subsets of a set A is a partition of A if number 1. S intersection S dash equal to empty. If S and S dash are in S and S not equal to S dash. Number 2. A equal to union S such that S belongs to S. If S is a set with an equivalence relation R, then it is easy to see that the equivalence classes of R form a partition of the set S. More interesting is the fact that the converse of this statement is true. Partition theorem. The equivalence classes of an equivalence relation on A form a partition of A. Conversely, given a partition on A, there is an equivalence relation with equivalence classes that are exactly the partition given. Such decomposition is called a partition. For example, if we wish to identify two integers, if they are either both even or both odd, then we end up with the partition of the integers into two sets, the set of even integers and the set of odd integers. The converse of theorem allows us to create or define an equivalence relation by merely partitioning a set into mutually exclusive subsets. The common attribute then might just be that elements belong to the same subset in the partition. Partition theorem. If R is an equivalence relation on a set A, the set of equivalence classes of R is denoted by A given R. Proof. Suppose R is an equivalence relation on A and S is the set of equivalence classes of R. If S is an equivalent classes, then S equal to A for some A belongs to A, hence S is non-empty since A related to A by the reflexive property of R. By partition theorem 1, if S equal to A and S dash equal to B, or in S, then A equal to B, if A intersection B, 6 equal to pi. Since this is biconditional, this statement is equivalent to A not equal to B. If A intersection B 6 equal to pi, since each equivalence class is contained in A union S such that S belongs to S subset of A. But as we just saw, every element in A is in the equivalence class it represents. So, A is a subset of S such that S belongs to S equal to A. This shows union S such that S belongs to S equal to A. Conclusion. In this chapter, the user have covered the following aspects of sets, relations and functions. Sets, subsets and operations on sets, finite and infinite sets. Relations and properties of relations, equivalence, compatibility, partial order relation, poset, least upper bound, greatest lower bound, maximal and minimal elements of a poset. Functions, inverse functions, composition of functions, recursive functions.